So this is on page 18, is that correct? Okay, so we're looking at page 18. We're looking today at mainly frictional forces, but in order to understand them, we have to review what we've already learned about normal forces. And then we're going to be determining the force of friction acting between a mass and a horizontal surface, or solving problems involving that. And the key phrase in this lesson is horizontal surface. If I have an object on a horizontal surface, there's an amount of friction there. Do you agree that if I try to push an object across a horizontal surface, it requires effort? That's because I have to overcome the force of friction. If, on the other hand, I have an object on a non-horizontal surface, let me just grab a block of wood. I didn't have time this morning. So if I have an object on a horizontal surface and I want to push it, I have to overcome friction, yes? Let's say in order for me to move it at a constant speed, I have to apply a force of 3 newtons. That would mean the force of friction is 3 newtons. Would you agree, and I'm not going to do it because it might get away from me, that the force required to keep this object moving here would be less? And just to exaggerate it, would you agree very little force would be required to get this to move? So the amount of the force of friction is different for an incline than it is for a horizontal surface. And an inclined surface, which we call an inclined plane, is more complicated. So we're starting today with simple horizontal surfaces. Okay? So I'm going to review with you officially what a normal force is. We talked about normal forces in the course of some lesson. I can't remember which. I think it was Newton's second law, where we were adding forces together. And we had a force of gravity down, but that was counteracted by a force upwards, called the normal force. So when an object is on a surface, there is a force between the object and what it is resting on. That force is called a normal force. We give the symbol F sub n for it, and it's the force acting on the object perpendicular to the surface. The explanation for this is that there is a normal force pushing me and the chair away from the earth, because I know there is a force of gravity pulling me and the chair towards the earth. But since I don't accelerate towards the earth, Newton's first law says the vertical forces must be balanced. So that force upward is what we call the normal force. Question: consider a mass just at rest on a horizontal surface. Why is the normal force equal in magnitude to the force of gravity? And I've pretty much answered this already. Somebody want to paraphrase what I just said? Ephraim? Right, there's no vertical acceleration, which means the forces vertically must be balanced. And quite frankly, it doesn't matter whether I use a vector symbol here or not, because 0 is 0. But if the acceleration is 0, and it is because the object is at rest, since a equals 0, F net equals 0. And this is really kind of a statement of Newton's first law of motion, but now you should understand why that's the case. Because F net is ma, and if a is 0, F net must be 0, because the mass times 0 will give you 0 newtons. And that means the forces are balanced. And that means, since we know there is a force of gravity acting towards the surface of the earth, pushing the block against the surface it's resting on, there will also be a force opposing that motion, perfectly in opposition to it. So these two forces have to be equal but opposite. Just to finish this off, that means that Fg and Fn, okay, we're back to the same question that I'm going to keep asking you. Is that a true statement? No, it is not. Is it true now? Yes, it is. These are equal. So this is Fg, and this is Fn. A question for you here, and I don't include this in your notes, but I think it's worthy of a little bit of a discussion. Would this also be the case if the object were accelerating horizontally? Yes, it would, because there's no vertical acceleration. Would it be the case if it were moving horizontally at a constant speed? Yes. All that is important is the acceleration vertically is 0. So from now on, if you ever need to find the normal force for an object on a horizontal surface, you can calculate the gravitational force instead. This is a big deal. This is saying that this is always the case on a horizontal surface. So now let's talk about frictional forces. When two objects are in contact with one another, there's what we call a force of friction, which will always oppose any motion. It's like this magical, all-knowing force that if I take this block of wood with this cup of sand and I push it to your right, the force of friction pushes back to the left. If I push this to the left, the force of friction opposes the motion and pushes to the right. The force of friction always opposes any applied force or motion. I don't want to imply that force and motion are the same. I'm just saying if an object is moving one way, the force of friction is the opposite way. If you're pushing an object one way, the force of friction is the opposite direction. This needs to be discussed, but I don't know what your world experience is with moving things around on surfaces. But how many of you have noticed that when you go to push, usually you'll notice it with a large, heavy object across a floor, the force required to get it to start moving is usually more than the force required once it is moving. Is that something you've experienced? Well, what that means is that there's a force of friction you have to overcome initially that's a larger force of friction than the force of friction you have to overcome when it's already moving. And we have names for those two forces of friction. So generally speaking, the force of friction is greater if they're not moving. That totally breaks down when you talk about friction with air. There's very little friction with the air here, but as I move faster, the friction goes up. So there's exceptions to this. There's something called a static frictional force. And the word static in science means, and humanities, means unchanging. And what it means in this case is the static frictional force is the force that you have to overcome, or the force of friction, when the object is stationary. So if it turns out that I have to push on this block of wood with the cup of sand, I'm pushing, I could be just practicing my miming skills, but will you believe me that I'm pushing on this a little bit? And I push a little bit more, and I push a little bit more, and then finally I get to maybe 3 newtons and it starts to move. That means that the force of friction is 3 newtons. Because when I was pushing with 2.9 newtons, nothing happened. But then once it does move, I might only require 2.5 newtons of force to cause it to move. So that friction is less. The static frictional force is the amount of friction present in a stationary situation. Once the object is in motion, there's still a force of friction, but it's usually less, and we call that the kinetic force of friction. The word kinetic means moving or motion. Sometimes you call this the dynamic force of friction. So there are 2 forces of friction here. They are related to the normal force acting on the object. So let's start with this very simple question. A 7.6 kilogram object is on a horizontal surface. What is the normal force acting on the object? We don't have a formula for normal force. This is something I want to really highlight for you. You will not find anywhere on your formula sheet something that says F sub n equals. You see F net, but F net is not the normal force. We do not have a formula for this. So how are we going to find out what the normal force is? Does anybody know? Yeah, Gabrielle. I'm going to just tweak that a bit and not talk about acceleration, because this is an object that may or may not be accelerating. And even if it is accelerating, it may not be accelerating at 9.81, because it's on a surface, so it's not in a free fall. But the word opposite and force is what's important here. That there is a gravitational force due to the gravitational field of 9.81. And you can say meters per second squared if you want, but I like newtons per kilogram. There's a gravitational force acting on the object. It's on a horizontal surface. If there's a gravitational force acting on the object, the horizontal surface prevents the object from moving in the direction of that force. Which means there has to be an equal but opposite force up, which is called the normal force. So the answer to my question is, in this case, because it's horizontal, and that changes if we angle the ramp or angle the surface. In this case, we can calculate the gravitational force, and that number will be the value of the normal force. So Fg as a magnitude is the same as Fn. This is a really important thing. This is what we answered in that first question. So if you ever need Fn, you don't have a way to calculate it directly, calculate Fg instead. And that's why we learned how to calculate the force of gravity yesterday. So the magnitude of the force of gravity on this object will be mg, which will be equal to 7.6 kilograms times 9.81. And, you know, again, I just said, if you want to use meters per second squared, you can, because that will give you the correct units of force. I just prefer you to use 9.81 newtons per kilogram here. And you're going to get approximately 76 newtons. While I'm moving my calculator over to this screen, you go ahead and do the calculation for me, please. It was 7.6, wasn't it? Thank you. You're getting about 74.6 newtons. Now, to answer the question in a technically correct manner, what we have found is that this is 74.6 newtons, which means this is 74.6 newtons up. I don't think we really need to worry about that, but I do want to highlight the idea here that this normal force is not the force of gravity. It has the same magnitude as the force of gravity, but it is up and the force of gravity is down. Are you with me on that? It may seem like I'm just steamrolling over the same idea again and again, but that's how important it is. All right. So I want you to think carefully about the two things that will determine how many newtons of force of friction there are between two surfaces. And there are only two things. In every scenario we can think of in the universe, the amount of friction between me and the floor, and the amount of friction between this block of wood and the desk, and the amount of friction between my shoes and the shingles on a roof are all determined by only two things. And I'm asking you to see if you can come up with what they are. And this is kind of a brainstorming thing where, usually people don't go, oh, that's that one, and they get it right away, and then somebody else says, oh, there's a second one, and we're done. It's going to require some discussion, maybe. Sam?
The one being like the mass of like the thing.
Yes and no. Let's talk about that so you can get a better understanding of what I mean by only two things. Would you agree that there is an amount of friction between this block of wood and the desk? And there's a certain mass here. It turns out it's a little over a kilogram. Would you agree there is a different amount of friction between the objects now, but the mass is the same? So I know you're used to thinking, well, if you change the mass, the force of friction will change. That's true. But we can get a different force of friction with the same mass on these surfaces. So it's more complicated than that. Forget about the object itself. What about the surfaces? Ephraim, what were you going to say? Were you going to say the mass?
No, I was thinking maybe acceleration. I was thinking maybe acceleration.
You're technically correct, but we don't want to go there. When you have objects moving at different speeds or accelerating, it may change the force of friction, but we would never analyze it that way.
So it's like what angle it's at?
True. What changes? So this is what I meant by brainstorming. This is not a simple question. What changes here when I change the angle? Yes, we could put the angle above the horizontal. That's correct. But we do something else instead. What is different in this scenario compared to this scenario other than the angle? In other words, if I incline this up, what changes? The way that gravity is hitting. And this is really tricky now. Gravity is acting vertically downward here, and not as much gravity is pushing this against the desk, which means the normal force is less. So it's actually the normal force. If I had a fairly icy sidewalk, I could probably walk around on it. But if I had that freezing rain on a roof, forget it. I wouldn't even make it on the roof. I'd take one step off of the ladder and I would lose my grip. And it's because the normal force, which is kind of the force between me and the roof, is different when it's angled than when it's not angled. So it's going to be the normal force. And over the course of the next 3 lessons, you're going to get a better understanding of this. It turns out that the force of friction is proportional to the normal force. And, if you go to your textbook, they probably just come right out and tell you that. And I could have just told you that in your notes, but I want to get you thinking about things. And I like that Sam said the way gravity is pushing the object against the surface. That's paraphrased, but you were talking about the fact that gravity is always acting down. And I'm going to hold this. Would you agree that the full brunt of gravity is pulling this whole block against the surface, whereas here gravity is pulling very little towards the surface? That amount that gravity pushes against the surface is the amount that the surface pushes perpendicular on the object, which is the normal force. So it's the normal force. There's another one, which I'm actually a little surprised that nobody said the other one first. Well, that is the force of friction. Yeah, so if you say, well, the force of friction depends on how much you need to push it, how much you need to push it is the force of friction. So we're not really getting anywhere there. Yep, Maxime?
Like some surfaces are not so like smooth.
Right. Some surfaces are not so smooth compared to others. So it's actually the nature of the surfaces. If I took some sandpaper and I took the gritty side of the sandpaper and put it up on this block of wood and glued the sandpaper on there, so the wood then becomes very rough. And I did the same to the desk, would you agree that I could probably move it like this and it wouldn't slide off? You have better traction on gravel that's been rained on with freezing rain than you do on a skating rink that's been rained on with freezing rain. So it's the nature of the surfaces. And I'm going to just make sure that you understand here, it's both surfaces. I hope you would agree that a block of ice on a skating rink has less friction than rubber-soled shoes on a skating rink. Okay. Well, there is I guess it's a parameter. I'm stuck in math mode right now. There is this quantity, which is a numerical measurement of the slipperiness or the relative slipperiness or stickiness of the surfaces. And this is called the coefficient. This is called the coefficient of friction. And in a little bit, you will learn where it comes from. It is what we call in science and physics an empirical item. If you want to determine the coefficient of friction between rubber-soled shoes and ice, you have to do an experiment to find the value. It's not something you can calculate theoretically. Okay? If I want to know the coefficient of friction between this wood and this laminate on this desk, I have to do an experiment. And this is, in fact, this experiment you're going to do tomorrow, except you'll probably use the countertop. This is a Greek letter pronounced mu. Okay, that's how it's pronounced. Before I go on, I'm surprised nobody said the surface area. And it turns out the surface area doesn't create more friction. You know how you have race cars with very wide tires? People think that's because the wideness of the tire produces more friction. It doesn't. What the wideness of the tire does is spreads out the amount of force acting on the tires to a bigger area, and they last longer. That's all it is. It has to do with making the tires last longer. So this is the Greek letter mu. And I'm going to come back to this formula, but in the meantime, I was in Greece a couple of years ago, and there was this cat hanging around on my balcony. Come on, that's got to be worth something. It's what a Greek cat says, mu. I shouldn't have had to explain it, but that's okay. This is the relationship. If you take the coefficient of friction times the normal force, you get the force of friction. I told you a little while ago that mu is an empirical thing. It's measured. Well, if you rearrange this, it's the amount of the force of friction over the normal force. So if the normal force is 100 newtons, for whatever reason, if the normal force is, say, 100 newtons, and you hook a spring scale to that object, and you start pulling on it and pulling on it and pulling on it, and then when it finally starts to move, it says 75 newtons, then the coefficient of friction is 0.75. The force of friction, no, I'll do it this way. The coefficient of friction is really the proportion of the normal force that gives you friction. And if you were to look on page 183 of your textbook, there's a table that shows various forces of friction, or coefficients of friction, rather. So if you were to look on page 183, you get this table that shows coefficients of friction. There's static friction and kinetic friction. Well, let's just talk about kinetic friction. When you take a look at, say, copper on copper, the coefficient of friction is quite large. It's 1, which means if the normal force is 100 newtons, it's going to have a force of friction of 100 newtons. If you look at something like a curling stone on ice, if you've ever curled, you know those curling stones are heavy, right? But it doesn't take much to get them to move. It's 0.002, which is 0.2%. Whatever the normal force is, the force of friction is only 0.2% of that. And these are all empirical. And you can see, looking over these, that the coefficient of static friction is in most cases, maybe all of them, more than the coefficient of kinetic friction. Except for Teflon on Teflon. It's the same. Okay. So let's do some problems together. A 7.6 kilogram object is pulled along a horizontal surface. The kinetic coefficient of friction is 0.2. What's the force of friction? Well, you know what? It doesn't matter whether you're moving the object or not, because the force of friction has a magnitude of mu times the normal force. I hope you're okay with me not putting vector symbols and absolute value signs. So, what is the normal force? I'm not asking you for a number. I'm saying, how do you find the normal force?
It's
The force of gravity. Because, and I'll draw it one more time, on a horizontal surface, that force of gravity acting down and the normal force acting up are equal in magnitude. So this is Fg, this is Fn. So Fn is Fg. Is this a true statement? Sure it is. I'm not saying vectors. I'm saying the magnitudes here, right? So what we do is this. In this question, we do that. Because Fg can be found by using m times g. Do not memorize this as if it's always going to be mu mg. The force of friction will always be mu mg if it is on a horizontal surface. That's true. But if it's not, then it's not. And that's it. We put the numbers in. Mu is 0.2 times 7.6 kilograms times 9.81 newtons per kilogram. .9 newtons. So that would be the force required to keep it moving. To keep it moving at a constant speed. If you apply less than that, it's going to start slowing down because the force of friction is greater than that. If you apply a force greater than 14.9 newtons, then the object will start to accelerate in the direction of its motion. 25 kilogram block is initially at rest on a rough horizontal surface, and the force of friction on that surface is 75 newtons. Let's break this down. It says a horizontal force of 75 newtons is required to set the block in motion. So that's a force of friction. Be very careful here. This is subtle. That 75 newtons is an applied force. But if it starts moving when you hit 75 newtons, then that must mean you're overcoming a frictional force of 75 newtons. While it's in motion, you can ease up and apply 60 newtons of force, and it will move at a constant speed. If it's moving at a constant speed, then that force you're applying has to be balanced by the force of friction. In other words, the force of static friction is equal to 75 newtons, and the force of kinetic friction is equal to 60 newtons. What are the coefficients of friction? That's pretty easy. Mu is equal to the amount of the force of friction over the amount of the normal force if you look up here just for a second, this diagram I have here, this I believe was the third time we've seen this diagram today. I'm not going to be drawing it all the time. What I'm going to do is say that since it's on a horizontal surface, we can calculate this instead by doing that. Because the amount of the normal force and the amount of the force of gravity are the same amount. And that means I can take for the coefficient of friction here, 75 newtons divided by 25 kilograms times 9.81 newtons per kilogram. And we should have learned enough by now for you to know that if you're going to divide this, you better put that denominator in brackets or calculate that denominator first and then divide. And over here, we're going to have mu equals 75 newtons over 60 kilograms times 9.81 newtons per kilogram. And you know me by now, I would probably just, because of how I was taught to do stuff on my calculator, I would probably take 25, I would probably take 75 divided by 25 divided by 9.81. I don't care how you get it. Are you getting 0.31? Okay, we do the same thing for the other one. This time it is 60 newtons, so we're going to have a smaller coefficient of friction, 0.24. Put roughly, what that means is that when the object is moving, the force of friction is about 24% of the normal force. The force of static friction is about 31% of the normal force. Is everybody getting those numbers? I'm just seeing a couple maybe puzzled faces. No? All right. Yes, Sam?
Does mu have units?
Pardon me?
Or like,
Oh, good question. Does mu have units? No. It is what's called a pure number or a unitless number because of this definition. Like, I'll look on your formula sheet in a second to see which way it's written. I think it might even be written this way. So when we determine mu, we measure a normal force somehow, probably by calculating the force of gravity on a horizontal surface. And then we measure the force of friction, and we take newtons divided by newtons, so mu has no units. Another way to look at it is if we just pick on this right here, Sam. When you look at the bottom, kilograms times newtons per kilogram will give you newtons, and we have newtons divided by newtons then, which is no units. It's a unitless number. Yeah, good question. Coefficient of static friction between a 10 kilogram object and the floor is 0.5. What is the maximum horizontal force that can be applied before it starts moving? Well, you need to understand, and this might be overkill for some of you, but I would rather that be the case than people not getting it. Let's just say that you are going to pull the object this way. And you can decide to draw this or not. If you are drawing it, maybe hold off on the arrows in a second. So this is an applied force. What if I told you that it doesn't move? Why does this object not move even though I'm pulling it to the right? Well, because there's a force of friction in the other direction, and I'm not meeting the force of friction yet, right? So let's just say that the force of friction, and it's a static force of friction, is that amount, okay? Do you understand why this applied force doesn't get it to move? I hope you do. Do you understand that this applied force will cause it to move? So the force that causes it to just move is when I just exceed that force of friction by even a microscopic number. In other words, in this case, when you look at this formula, force of friction equals mu Fn, and I'm going to leave the vectors out of it, you're asked for the force of friction. It says, what is the maximum applied force that you can apply? Well, that's the same as asking what's the force of... Is that what you were wondering about, Ephraim, that this is... no, static was right. It's asking what is the force of static friction. They're the same thing in this question. So we're calculating the force of friction, which is mu mg. Why is it mg? Because of this. So you're not asked directly what's the force of friction, but if we find the force of friction, that is the answer to the question. How do you calculate the force of friction? Mu Fn. Well, we can't calculate Fn directly, but it's the same as the force of gravity. That's why all these subscripts mean things. So if we take 0.5, if we take 0.5, which is mu, we multiply that by 10 kilograms, we multiply that by 9.81 newtons per kilogram, we get the force of friction, which is the applied force needed to get it to move, 49 newtons. It's all about substituting in different forces for forces that we need to use or find because they happen to be the same. Yep.
If you put that force, it will move or it won't?
Yeah, and that's a interesting thing. You remember when I said, so you have to apply a force, I think the words I used were a microscopic number more than the force of friction. So
you have to say like a teeny bit less than the actual answer.
we would never answer it that way. We would never answer it that way. So, but you are right. If I said, what is the force of friction? And let's say it worked out to exactly 49.05 newtons. That's the force of friction. What is the force needed to get it to move? 49.050000000001 would be, in theory, the force. We don't need to worry about that, though. And the last question. 5 kilogram block is moving with an initial speed of 22 meters per second. It encounters a rough surface where the coefficient of friction is 1.15. How far does it take for the block to stop? So what we're dealing with here is a smooth surface and then a rough surface. And the object is moving at 22 meters per second when it first encounters the rough surface. That's a VI. That's a VI. Why will, in your own words, who can tell me, why will the block stop? There's no internal brakes here. There's nobody in there hitting the brakes. I'm not hanging on the left side of this with a rope trying to slow it down. Why does it stop, Ephraim?
Because the friction increases. Force of friction increases.
By increases, you mean as soon as it hits that dark area, there's a force of friction that's going to slow it down. Right. So you're saying increases compared to what it was here. We're not even going to worry about what it was there because it's at this point in time that VI is 22. It might have actually been 24 and slowed down a little bit, and then it hits the really rough surface. But the answer to the question is the net force will not be zero. Will there be a force backward? What do we call that force? Force friction. Are there any other forces acting on this object? Well, yeah, there's a force of gravity. And there's a normal force. Are you guys on board with me when I say, yeah, but who cares? Well, we do care a little bit because that's going to tell us that the normal force is the same as the force of gravity in calculation form. Okay, let me write something down for you. Think about that carefully. When I write that, I'm not claiming this is something you should memorize. But in this question, is that a true statement? Turns out it is. What do you get when you add these three forces together? You get the force of friction. These three forces added together give you the force of friction. So the net force is the force of friction. Which means we can do this. On our formula sheet, and this is what I've been talking about for 6 weeks now, how we build formulas in high school physics. On your formula sheet, F net can be found using MA. Force of friction can be found using mu Fn. Correct? This is actually a formula on your formula sheet, and this is a formula on your formula sheet. Right? But then you have to say, yeah, but these two things are equal in magnitude. So what I can do is I can say Ma equals mu times the gravitational force without regard to direction. And then I can say Ma equals mu mg. And here is why you cannot confuse A with G. A is the physical acceleration of the object. G is 9.81. Why are we doing this? Because you know VI, you know VF, in order for you to find the distance, you need to know one other thing, which will be the acceleration. Incidentally, you don't actually need to know the mass. The answer to this question is going to be the same whether the mass of the object is 10 kilograms or 100 kilograms, which is kind of weird, but it's true. So we have to find the acceleration from this, and then we can put the acceleration over there and answer the question. What was the coefficient of friction was 1.15, and the mass is 5 kilograms. I'm going to leave the masses in, well, I don't know. Let me divide both sides by m to get the acceleration. If you want to put the mass of 5 kilograms in the top and the bottom, feel free, but they're going to cancel. So all we have to do is take mu times g. We get 11.2815 meters per second squared. And now we're transported back in time to kinematics. I guess Vf squared equals Vi squared plus 2AD. Zero squared. You know, and I'm putting units in pretty much all the time now. If it bothers you and you find you're more successful without it, then don't put them. You're going to get burned for half a mark on an assignment, okay, but you'll get the right answer. If it confuses you. So, I'm going to make one adjustment here. You'll never get this negative for the acceleration coming out of a formula. The negative is because the object is moving to the right, but it is forced backwards due to the force of friction. So the acceleration is negative. We need to take that 22 squared, subtract it to the other side, where it becomes negative, and then divide by 2, and divide by negative 11.2815, and get an answer of 21 meters. And that's the answer to the final example. This entire lesson is all about this formula, mu equals force of friction over normal force. Let's take a look at how it appears on your formula sheet. It will be under dynamics. So this is how it appears on your formula sheet. The magnitude of the force of friction equals mu times the magnitude of the normal force. You just have to remember, for a horizontal surface, the normal force has a magnitude that's the same as mg, the force due to gravity. Okay? So you got some questions to work on for tomorrow. Tomorrow we will go over any problems that you have and then do a lab where you determine the coefficient of friction between a block of wood and the countertop. Yeah, of course.